Hi everyone, welcome to Astronomy. This week we'll have Ben Coughenour speaking. He's currently a postdoc at the Space Sciences Lab here at UC Berkeley, working on X-ray telescopes to study black holes, neutron stars, and white dwarfs. He completed his PhD at Wayne State University in Detroit, Michigan, and will begin a professorship at Utah Valley University beginning this fall. He's also been a volunteer with us for a few years, and we're excited, though we're sad to see him go. So also, if you look outside, it is extremely cloudy, so unfortunately we're not going to get to
No sky July.
Sorry?
No sky July.
Yeah, so we'll just have our lovely talk. All right.
Cool. Thanks, Natasha and Natalie, and just generally the Astronomy team coming in, folks. Yeah, I will say it's been a lot of fun coming to Astronomy, whether it's just to set up telescopes upstairs or just listen to the talks. I've enjoyed it a lot. I'm also pleasantly surprised to see so many people in the room tonight, given that the weather looks like it does. I will say no sky July. I'm from Michigan, so it's like no sky all the time. But yeah, this season's been a bit of a bummer, and I hope you guys get clearer skies. This is my last Astronomy, but as we get into August and September and October, you actually get to look at the telescopes upstairs. But for tonight, we can just sort of talk a little bit about research that I do / people I've been fortunate enough to meet get to do, and sort of I think a cool project that a number of different groups are working on, and sort of a target and a question that people are trying to answer and constantly one-up each other in a fun way. So the talk's called Probing the Mass Limit, finding and measuring the most massive white dwarfs known. And what we'll talk about, looks like I have to click. We'll talk a little bit about just what a white dwarf is, and how they come about. That relates to our sun as well, if you happen to care what happens to our solar system in 5 or 6 billion years. And then I'll talk a little bit more about some of the research that friends of mine have done and that I've done as well, chasing down some peculiar and unique massive white dwarfs as well. And at the end, if I have time or if I don't run over time, it's always good to talk about why do we care? And a lot of the time, my answer is just because it's cool. But this time, I actually think I have some good answers for that question as well. So just to start, what is a white dwarf? Quick show of hands. How many people have heard of white dwarf or think they know what a white dwarf is? You guys seem to be pretty interested in astronomy, and you came to this talk. That's a lot of you. So you can just fall asleep for the next 10 minutes then. But what a white dwarf is, we can think about our sun. I'm lucky enough to work at the Space Sciences Lab, and this is the view when it's not cloudy, and we get a good sunset. But there's our sun sitting over San Francisco in the Bay, and our sun is a typical star, which is neat because it's the closest to our star to us, and it's the easiest for us to study. And we've learned a lot about the sun, so we can draw cool diagrams. It's always worth looking through a solar telescope if you ever get the chance to look for sunspots or filaments around the edge of the sun using the proper filters. But what we're going to focus about is just where does all of this light come from the sun, and that has to do with processes that are taking place at the core of the sun, where our sun's a huge object. There's tremendous pressures and densities within that core, so much so that you can essentially take multiple different hydrogen atoms and squeeze them together to form helium. The process is a little bit more complicated than that, which I've shown on the right here, but you start with 4 hydrogen atoms, which are their nuclei essentially are just protons, and through a few different interactions and a few different steps, you end up with a helium-4 nucleus at the end of that. It turns out that helium-4 nucleus weighs ever so slightly less than the input 4 hydrogen atoms. So just with E equals mc squared, you get a tremendous amount of energy from that. And also, because our sun is huge, it's doing that process a ridiculous number of times. I went through the calculation yesterday. I've already forgotten how many times per second it happens, but about 600 million tons of hydrogen is being converted into helium every second within the core of our sun. And when you consider how small a proton is, that's a whole lot of interactions. Most stars do this. In fact, this is sort of what defines a star, is at its core, it's fusing lighter elements into heavier elements. Depending on what those elements are, it always starts with hydrogen into helium and then up to heavier elements. But the main idea is this is where starlight comes from. You might fuse different elements at different phases of a star's lifetime as well. And you can kind of sum all of a star's lifetime through stellar evolution in this one crazy poster that used to be hanging on the wall of my astronomy lab back when I taught astronomy labs. And just to kind of read this, time goes from left to right. So you start with a molecular cloud on the left where the stars are born and then they live their lives and die as you get to the right. And how a star lives its life and dies depends on its mass. So the most massive stars are at the top. The most sort of regular or smaller mass stars are at the bottom. And our sun is sort of a typical fairly common star right in the medium of that mass distribution or the middle of that mass distribution. And if you look to our sun's lifetime, it began as a protostar, as all stars do. It will live for about 10 or 11 billion years as we call a main sequence or a normal living star. It will eventually run out of hydrogen fuel, pop up into a red giant, blow away its outer layers over a few thousand years into a planetary nebula, and then leave its core behind as a white dwarf. And just as that red giant phase, when our sun does run out of fuel, it's going to pop up multiple orders of magnitude, or an order of magnitude larger than it currently is. So this is a typical red giant compared to our sun per scale. We can also look at lots of different stars, and even though this process takes billions of years, we get to see it at different phases. So here are some similar sun-like stars along different points in its evolution, again, to scale to give us an idea of how big that popping up will be when our sun does run out of hydrogen fusion and starts fusing helium into carbon and oxygen later on in its life. And then it will do some hydrogen fusion in different shells. And it's a whole long, complicated process as our sun becomes a red giant and before it blows away its outer layers. But I like it summed up best with this comic because it does involve us too, in a way, if we were still around at least. Our sun getting sick, turning into a red giant when it runs out of its normal fuel. And unfortunately, as it expands into a red giant, it will engulf, in the first phase of being a red giant, it will engulf the inner two planets, Mercury and Venus, and then sort of wobble a little bit and then come back out for Earth as well. So there's our very sad, very sick sun late on in its life. After that has happened, towards the end of that somewhat unstable and relatively short-lived red giant phase, our sun is going to puff out most of its outer layers into the surrounding area. And this is one of the coolest sort of sets of fireworks, and some of the most beautiful images that we have are having seen stars that have done this within the last few thousand years. And we can see the remnants, the outer layers of those stars surrounding what was left of their core. Yes, question in the back.
Yeah, this might be kind of tangential, but why does it get so much bigger when it turns into a red dwarf?
It's a great question, and one that I probably can't get into with a long answer, but the short answer is it's fusing hydrogen into helium within different shells around the core after the core is either done fusing those heavier elements or afterwards. And it's a crazy, all those different fusion reactions happen at different pressures and temperatures. So it's a crazy balance between gravity, always wanting to squeeze the star down, and that intense radiation puffing the outer layers of the star back out. So it's a bit of a balancing act between that and what layers and what shells that nuclear fusion is still happening within the red giant. Yeah.
What is a word question? Why is it called a planetary nebula when we think of a star as not a planet? So why is it planetary? And the second question is, how long generally does the red giant last?
Just to get the second question, a red giant's phase, I think for our sun will be on the order of 10 to 100 million years, okay, which over our 10 billion year lifetime for a star like our sun is pretty short. And for more massive stars, even shorter. Okay. As to the first question, why is it called a planetary nebula? I did put it somewhat in quotes. That's a great question. It's because astronomers are terrible at naming things. When we first started seeing these clouds around stars with longer exposures or just as sort of faint wisps through a telescope with the naked eye, but astronomers didn't know what had caused these. And there was an idea that we knew our solar system existed around a star, and we see these clouds around a star, that might be how solar systems form around other stars. So planetary nebula, we were thinking these were the seeds of planets around a newly born star. It's exactly the opposite. If there were any planets around these stars, they're long gone, and these are the outer levels of that star around the remaining dead star.
Okay.
So great question. So see, these are some of the more famous nebula that we have, these planetary nebula that are indeed dead stars that were somewhat like our sun. We have a few more pictures. Most of these are with the Hubble Space Telescope and some other composites, sometimes from Earth-based observing or otherwise, but just some beautiful images here. And the case is always the same. At the very center of this cloud, you have the leftover core of the star, the inert, mostly carbon and oxygen that's left over from a short bit of helium fusion that happens in the core of the star during that red giant phase. And that leftover core, once you get the beautiful fireworks out of the stage or out of the way, is what we call a white dwarf. And just as an example, here's a system of two stars. One is a main sequence star, a living star like our sun, next to its white dwarf, which is labeled B here. And for comparison, we have our sun as it is today. And you can see the white dwarf is much smaller. That's the leftover core from a star that would have been living next to and in orbit with Pegasi A here. That was an artist rendition. Here's an actual image of one of the first white dwarfs that we've been able to directly image, and one of the first that was discovered, which is Sirius is the brightest star in the nighttime sky. If you look for very, very close to it with a powerful enough telescope and with enough focusing to be able to resolve the two, you can actually see a secondary star right next to it, which is known as Sirius B, which is a white dwarf companion to Sirius A. This was identified in the early 1930s. The first isolated white dwarf that didn't show up next to a companion star like this wasn't discovered until 1917, and many more were discovered later. And actually, astronomers began to realize that some stars we didn't know were white dwarfs were actually white dwarfs upon doing further analysis. Yes.
So atomically, they come across it very small, but gravitationally, there's a lot of mass in it, right?
There is indeed. These are still closer to stars than planets, despite their size being closer to that of a planet.
So in a binary,
These would still probably orbit each other. I don't know off the top of my head. These probably have similar mass. Interestingly, Sirius B would have been the more massive star in the binary when it was born. You can sometimes have mass interchange, but the more massive stars actually live and evolve faster than the least massive star. So Sirius B would have been brighter at one point. It would have lived its life and now is just the remnant white dwarf, so it doesn't appear as bright as its companion. But yes, we'll talk about masses of white dwarfs, since that is what we're here to do specifically. But I have to take a side note just to talk about these binaries. I mentioned you can find isolated white dwarfs, but white dwarfs in binaries is how we often see them. And it's because we're looking at a particular star, we're noticing that star wobble. It's almost like how we look for planets around stars today. But just side note, generally, whether it's a white dwarf or not, most of the points of light you see in the nighttime sky, or at least half of them, are not single stars, but actually typically binaries. You could also have triplets or quadruplets of stars all orbiting around a collective center of gravity. So our sun is actually almost unique in that sense, that it doesn't have a partner star or a companion star. One of my favorite examples of this is Polaris, the North Star, is actually not just a binary, but a triplet. Polaris A and AB orbit one another in a close binary, and then Polaris B orbits that center. So these are three stars that are gravitationally bound to one another. And we actually see that thing pretty regularly. So actually, George Lucas had it pretty much right. You could very well imagine, and it wouldn't be too out of the usual or too unexpected, to imagine living on a planet with two suns. Most suns have another sun, or at least half of the what we see as individual stars are often more than just one star. I mentioned isolated white dwarfs, and I have to show pretty pictures because that's the best part about giving a talk. And with Hubble Space Telescope imaging and different cameras on the Hubble Space Telescope, these are some zoomed in images of a bright globular cluster, which itself has hundreds of thousands of stars. But zooming in, you can actually see in between those bright points of light, very, 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 very faint points of light in between them. These are isolated white dwarfs within the dense cluster that is this globular cluster. This is M4, so you can actually see this globular cluster with binoculars if you know where to look for it. But those aren't distant stars. Those are actually just very, very, by size, very, very small leftover cores from stars that would have once been living within this globular cluster. So we have this core collapse. White dwarfs aren't typically stars in that there's no longer nuclear fusion anymore. So you're depending on exactly how you define a star, they're not necessarily living anymore, or they're not necessarily stars anymore. When a star lives its whole lifetime, like our sun is doing right now, what prevents the further gravitational collapse is that nuclear fusion. It's a tremendous amount of energy released by that process. But with the white dwarf, it's inert. You don't have any fusion. So where do you get this ability to fight back against gravity? And we have to get down to the atomic scale, and it actually comes from properties of quantum mechanics, which is a bit of fun, that are holding a white dwarf together. This is a fun little cartoon I made. It's not actually physically accurate, but it's still fun for illustrative purposes. The idea is there's a quantum mechanical principle, the Pauli exclusion principle, that no two, in this case electrons, but it works for other fundamental particles as well, can occupy the same quantum state. Well, in our everyday lives, that never matters because there's tons of empty space around us. There's tons of energy, whether it's thermal energy or otherwise. There's tons of different places for these electrons to occupy, whether that's just in different orbits around their atoms, or even just leaving that atom to join another. But in an extra dense environment of leftover core of a star like our sun, after that core has collapsed, these atoms get pushed so close to one another, and actually the electrons around those atoms get pushed so close to one another that they run out of different sort of orbits to jump back and forth in between. So as they get pushed and pushed and pushed, they can't occupy different orbits, and they get sort of squished into a current orbit. And as you push them, even compress them even further, there's a tendency for them to actually resist that, which is where this pressure comes from. And you can kind of think about it just like this. You're running out of space for these electron clouds around these atoms before they start intermixing and interacting, which just because they're not allowed to occupy the same state, they cannot do. Interestingly, this is a white dwarf. Electron degeneracy pressure, it is still normal atoms with the nucleus at the center made of protons and neutrons and electrons buzzing around. With a neutron star, you get an entirely different point of degeneracy pressure. It's the neutrons themselves. And a neutron star is almost like one giant atom. And it's actually the individual neutrons themselves with that same quantum mechanical principle, but on an entirely different energy scale and on an entirely different density scale, resisting further collapse. But just for us, for white dwarfs, we'll stick with that, this electron degeneracy pressure. And as a comparison with sizes, we have Earth, which I think we all have a somewhat okay idea about how big the Earth is. A sun-sized white dwarf would be right around the same size, or a star that weighs, a white dwarf that weighs about as much as the sun would be right about the same size as the Earth. A neutron star, for example, which would actually weigh more than either of the two of them, is condensed down to about the size of the city, which is that different scale between electron degeneracy pressure and neutron degeneracy pressure. Just to think about the scale a little bit more and how crazy it is without even getting to neutron stars, just how crazy white dwarfs are in and of themselves. Here are a few examples, all drawn to scale. And again, with our Earth, which is a pretty helpful reference point. It turns out that if you have a more massive leftover remnant core, a more massive white dwarf, well, the way degeneracy pressure works is that the pressure goes up the more it gets compressed. But it does take that extra compression. So if you were to add mass to a star, it would actually get physically smaller and denser. So of these three white dwarfs I'm showing, Sirius B is the most massive of them. It weighs just a little bit more than our sun, which, again, considering its size next to the Earth, is sort of an almost unfathomable thing. And to illustrate that, we're going to talk a little bit about scale. This is the Earth-Moon system to scale with the distances, and I know the moon looks very, very small, but that's the only way we can fit them on the slide at the same time. That distance is about 240,000 miles between the Earth and the moon. We can compare that scale to the sun. And they both fit well inside the sun. If the Earth was at the center of the sun, the moon would be, I don't know, 2/3 of the way out if it could orbit in that way. The sun makes up more than 99.9% of our whole solar system. So from an outside observer, it's pretty much just the sun. Most of that, less than 0.1%, is Jupiter for the rest of it. So it's incredible that you're taking that much mass and squeezing it down to such a small scale. And I think that gives us a little bit more insight on how ridiculous an object something like Sirius B is. Back to degeneracy pressure, though, I mentioned that the more massive you are, the smaller the object gets. The densities get higher as you add more mass. So here's a plot of the mass versus radius for a few different theoretical curves for how material at this limit would work. The difference between the non-relativistic gas and the relativistic gas, you don't have to worry about too much, other than the relativistic one is more accurate. As you squeeze things closer and closer and closer together, those electrons actually start moving more and more rapidly until they approach the speed of light, and then you have to worry about relativity. For a little bit of conception, here's Earth's radius drawn onto this plot. So as you get a star or a white dwarf that's about the size, or the weight of the sun, one solar mass there, where it falls along that relativistic line is going to be pretty close to the size of the Earth, as we just saw with the Earth, and in comparison, Sirius B. These two lines were first calculated by Subramanian Chandrasekhar, who was a brilliant astrophysicist, or at this point, I think just physicist. Similar calculations had been done before, but he took the relativistic route and came up with the sort of upper limit and calculated a more accurate upper limit for the possibility of how massive a white dwarf, that leftover remnant core of a star, could be. This actually got him into a fight with another famous physicist or astronomer who didn't like the idea that black holes could exist. And back in the 30s, nobody knew that black holes could actually exist as astrophysical objects. But the big point of contention was that ultra-relativistic limit, which on that chart is where the radius drops to 0. Of course, if you have a radius of 0, that's infinitesimally small, that's a singularity, and that's where you get into black hole territory, which caused Chandrasekhar a whole bunch of trouble. And sort of fortunately or unfortunately, depending on whether or not you want white dwarfs to exist, that limit isn't actually something that's often met in reality, because just before that, at about 99% of that upper mass limit of a white dwarf, something else takes over before you have a further collapse. If we didn't have to worry about this effect, it would just collapse into a neutron star or even conceivably a black hole. Instead, what happens is reignition. We're mostly left over with the ashes of the helium fusion that happened, for example, that will happen in our sun. Those are carbon and oxygen. But if you get to high enough densities and you get to high enough temperatures, you enter a realm where fusing even those heavier elements becomes possible. The difference is, in our sun or in a normal star, that fusion is balanced by the rest of the star. In a white dwarf, though, it's degeneracy pressure holding this thing together. And as soon as you ignite that fusion, it just completely burns up the entirety of the mass of the star into one ridiculous explosion. And it happens rather quickly. These are 3D simulations of white dwarf detonation at its core at the highest densities and temperatures, where carbon starts fusing suddenly to heavier elements. And that whole series of snapshots from this video is 1.2 seconds in time. So most of the mass of the white dwarf could ignite within just about a second or so, and be fused from carbon and oxygen into heavier elements. But there's one question before we get there, and I'm talking about putting mass onto a white dwarf or having a heavier and heavier and heavier mass dwarf, heavier and heavier and heavier mass white dwarf. But if you think about our sun, as it turns into a white dwarf, it's just going to be a white dwarf with the planetary nebula around it, floating out into space, and whatever leftovers of the planets are still there, and pretty much nothing around. So the question is, where does the matter come from? If we're talking about adding material, otherwise a white dwarf will just exist at whatever mass it was born with and never change, and you don't have to worry about any of these effects, and we wouldn't have to draw these diagrams. So my question to you, the audience, is, where would you get extra mass to add it onto a white dwarf? I hinted at the answer earlier, yes.
Another star.
Another star. Do you have a similar?
Binary.
Precisely right. I've talked about binaries before. Most stars don't live alone like our sun does. Many of them have binary companions. So if we wanted to get Sirius B some extra mass, well, looky there, Sirius A is right next to it, ready to provide that additional material. Most white dwarfs we find in binaries, and those can happen in sort of two different ways. You can imagine two orbiting white dwarfs if they were allowed to have normal stars like our sun that evolved and reached the end of their lifetimes. You could have two white dwarfs orbiting one another, given a long enough amount of time. And if you waited a really long time, you could imagine those white dwarfs merging. We've seen black holes merge, or I should say we've listened to black holes merge, so certainly the same thing could happen with white dwarfs as well. Or if you had a white dwarf that was in a very close binary with a normal star, it could, because of those extreme densities, start to pull material off of the outer envelope of that star. And that material forms what we call an accretion disk. We see this a lot with black holes and neutron stars, but it can certainly happen with white dwarfs too, where it starts cannibalizing its partner star. So there are absolutely astrophysical scenarios when you can add material onto a white dwarf. So now the question comes, where are we going to find and how are we going to find these ultramassive white dwarfs that are nearing that mass limit? And the first answer to that is a really brilliant piece of work that this paper was published in 2021 by a friend of mine who's visited Berkeley before. I had nothing to do with this though, so I'll throw up the headlines and just claim all the plaudits from my friend Ilaria, who wrote this paper. But in a bit of follow-up that they did, they discovered a white dwarf with a mass of 1.35 solar masses, or M-sun is what I'm referencing there. And that limit that we were talking about, the Chandrasekhar limit, is about 1.4 solar masses. So we're getting really, really close to that maximum possible theoretical limit here. And just how they went about doing this, here's a chart where we're seeing magnitude is the y-axis and color is the x-axis. You don't necessarily have to worry about that too much. But just the general idea is the further down and to the left you go, all of those dots that you see are different white dwarfs. And the further down and to the left you go, chances are you're finding more and more massive white dwarfs. So the most active objects are down and to the left. The project that Ilaria and this team worked on was they were using the Zwicky Transient Facility, which scans the entire sky, or at least the northern hemisphere of the sky every 2 days. And they're looking for variability. So if you're taking snapshots of a star over time and that star is changing in brightness, the ZTF will find it. And so by following up on all of these different white dwarfs and sort of doing a comb to look for variability, they found one star in particular that was of interest to them, and it's that red star on the bottom left of this diagram called ZTF 1901. Yes.
How many of those are isolated and how many are in?
Good question, and I don't know the answer to that. It would depend on whether or not they already did a comb.
Possibility.
Yeah. It would depend on whether or not they've done a comb to just look at isolated stars. So it could be all of them are isolated, and if not, less than half of them would be isolated. But I forget on what different filters they used before they got here. This star, as I showed the headlines earlier, in size, it's only about 20% larger than Earth's moon. And you can see how much of an outlier it is there all the way on the left. But it weighs quite a bit more than our sun, which is a pretty extraordinary thing. So here's an artist representation of that white dwarf next to our moon. But its giant size, or its mass, it's actually quite small. It's the smallest white dwarf where we've measured the radius of it. So its incredible mass and small physical size aren't the only things that are unique about this white dwarf. They also were able to measure the rotation of the white dwarf. That was the variability they were looking for. And it turns out that it spins every 7 minutes. It gets brighter and fainter on a 7-minute period. So this object, roughly the size of our moon, weighing 30% more than our sun, is spinning every 7 minutes, which, you know, Earth spins once every 24 hours. The sun takes like 2 or 3 weeks to complete one rotation. So it's a pretty incredible object in that sense. Also interesting was its magnetic field, about 1 billion times stronger than Earth's magnetic field. So ridiculously fast spin, even for a white dwarf, and a ridiculously strong magnetic field. And it just turns out that this is expected for a certain type of a white dwarf, and one that came from, or was born from, the merger of 2 white dwarfs. So this one used to be a binary. You had 2 white dwarfs that were orbiting one another, They spun up as they got closer and closer and closer, and that angular momentum from the orbit of those two white dwarfs got imparted to the remnant, which we see now, which is why it spins so quickly every 7 minutes. It's also worth mentioning that's where the magnetic field strength comes from as well. It just so happens that those two white dwarfs, when they merged, weren't massive enough to break that limit to get beyond 1.4 solar masses. Yes.
I believe you mentioned that there are no fusion processes occurring on white dwarf.
Yep.
So the light energy is coming through fission.
No, it's actually just remnant heat. They're so hot when they're formed, and the gravitational compression heats white dwarfs up to incredible temperatures, and they just radiate due to the core temperature. The core temperature can be in tens of millions of degrees or thereabouts. Yes.
Just for reference, what's the state velocity for Tennessee Open?
That's a good question. And I don't know the answer, but you could probably getting close to 1% the speed of light, maybe. Escape velocity, it'd be a big number, and the escape velocity is big for our sun, so it would be pretty big for a massive white dwarf. Yes.
I've read about a non-rotational white dwarf, and how is that important to note? Why is that important to note?
You would have to form a non-rotating white dwarf with a very particular star and the way it ended its lifetime. The winds of that star and the rotation from that star with its winds would have had to take away any of the rotation and any of the angular momentum, leaving a non-rotating core. So that says a lot about how stars live on in their late stages in that red dwarf process, and how the solar stellar wind comes off. But that's actually a really good question. I don't know enough about non-rotating white dwarfs. So well, there's one other point I wanted to make about our friends ETF 1901, which is just how they went about measuring this. So since it's a talk about measuring the masses of the most massive white dwarfs, how do you actually do that with this star? And in this case, they used really excellent photometric data. They could just measure very, very well how bright it is. From that, they knew its radius because they could also measure from its spectrum its temperature. And the last thing of that component, you know exactly how big something is because you've got its radius, and then you know how bright it is. All you have to know is how far away it is to relate that brightness to the actual mass of the object. So just from measuring the distance really, really well, this object did have a distance measurement. And for measuring its radius really, really well, which again just had to do with how bright it was and knowing how far away it was, they were able to come up with a pretty excellent mass estimate with 1.35 plus or minus 0.02. So within a percent or two of the mass of the star, which is, I think, pretty excellent. Number two on our tour of massive objects is an object that's been known about for a really long time. This white dwarf, Corona Borealis, was actually first seen in 1866 because it's a different type of system. This is actually a star that's a white dwarf that's hanging out right next to a red giant star, and it's actually eating its companion red giant star. There's an accretion disk, a stable accretion disk around this object. Every once in a while, as that material falls onto the white dwarf, it will heat up, but more importantly, that white dwarf is made of carbon and oxygen, but when you add hydrogen on top of it, if you add enough hydrogen on top of it, the temperature and pressure you need to fuse hydrogen is a lot lower than what you need around a white dwarf. So you can actually, in a flash, ignite all the hydrogen just on the surface, not the whole star, but just with around the surface. You could think of like lighting an ocean on fire. It will burn up the entire ocean or atmosphere of hydrogen and helium on that white dwarf, and we call that flash a nova, which distinguishes it from a supernova. It doesn't explode the entire star. This source was seen as a nova. It appeared as a brand new star in the sky, and tracing back, we can see it today, although when we look, we mostly just see the red giant, which sort of dominates just because of how physically big it is, what we see. Again, first seen go on to nova in 1866 and traced back and is pretty well studied today. This has been looked at, and in 2004, a paper came out that estimated the mass of this object to be 1.37. We're getting even closer to that 1.4. In fact, the upper limits from this estimate are consistent with being more than the Chandrasekhar mass. So depending on how reliably you trust that those good physics equations that calculated the upper limit, You could even set a stricter upper limit on this source. The way this mass was measured was just the Doppler effect, which I think is something we're all familiar with. As a car drives by you, its engine sounds higher pitched than when it drives away from you, which is why a passing car sounds like. Well, it turns out the Doppler effect matters for light too. And there's a really handy thing when you want to measure the mass of a star and you don't have better methods. The best thing you could do would be to drop an object around that star and watch how that object moves around it. And we can trust our laws of just Kepler's laws of gravity and orbits to be able to measure that mass. Well, thankfully for us with this star, there is another star right next to it. And by just tracking the movement of those stars using the Doppler effect, light from the star is redshifted as it moves away from us and then blue shifted as it moves towards us. And by tracking that motion as these two stars orbit one another, we were able to come up with a really good measurement of both of the masses within the system of the white dwarf and the red giant, which I think is a pretty amazing thing to be able to do. The last bit of ways to find really massive white dwarfs and to push that limit is switching to a totally different wavelength. Everything I've talked about so far, we're using normal optical light, but now we're going to switch into X-rays, which is actually what I do. So finally, I get to talk about my own research, at least a little bit. One of the things that when you have a star like T Corona Borealis, it's stealing material off its companion star. That material forms an accretion disk and falls down the gravitational potential well onto the white dwarf. It starts moving really fast when it does so. You can think about it like in free fall. Objects in free fall from outer space coming to Earth are going to be moving pretty quickly, especially if you didn't have an atmosphere to worry about. That's definitely true of material falling onto a white dwarf with much more mass than Earth. In fact, that free fall material, as it basically crashes into the surface of the white dwarf, heats up to tens of millions of degrees and shines in X-rays rather than shining in regular optical light or even in UV like our sun is capable of doing, blowing right up into the X-ray part of the electromagnetic spectrum. These systems, we call them cataclysmic variables. That's not just because of the X-rays, that's just because these are the types of systems that can go into those nova events where you see these flashes of all the material that then accreted onto or fell onto the white dwarf suddenly igniting all in one crazy cataclysmic event. But they survive those explosions and they continue to steal matter off of their partner star. That X-ray portion that I'm talking about only happens right near the surface of the white dwarf. So if you could imagine zooming in, you might notice that this disk that's around the white dwarf, it doesn't go all the way down. Often the white dwarf with the magnetic field, the magnetic field of the white dwarf will be powerful enough to control the free fall of that material from the inner accretion disk. So you'll have material that sort of falls in, piles in along magnetic field lines, rather than just sloshing right down onto the surface of the white dwarf. You can maybe kind of see that with a few different lines that are drawing material from the inner disk to the surface of the white dwarf. If you zoomed in, and you pardon my very crude graphic design skills, you have a column of material that's basically in free fall and then just crashing into, or the white dwarf surface, or actually crashing just above the white dwarf surface into a shock. And that's going to be the region where you're emitting the most X-rays. And that's the material that I get to study when I'm using X-rays to look at our sky. And when we do that, we're just going to take a step back and sort of think about what the sky looks like generally. Here's an all-sky map that was produced by Gaia, which is a spacecraft that's just constantly touring the sky, constantly taking images and measuring really precise positions of stars. But when we look at the sky in X-rays instead of optical light, where you're seeing these clouds of dust and most of that light is actually from adult stars, when you're looking at X-rays, you're suddenly seeing an entirely different picture. You're seeing a bunch of different points of light, and it's only most extreme objects that are able to get hot enough to produce X-rays. Some of these points of light are going to be coming from supermassive black holes and distant galaxies, but you can still see that they're more or less shaped like our galaxy. Just like how we saw the disk of the galaxy in the last image, that means that these are objects within the Milky Way. And a lot of these are going to be black holes or neutron stars in our own backyard that are stealing material off companion stars and shining brightly in X-rays. But as we know, white dwarfs can do that too. So some fraction of these sources are going to be white dwarfs that are actively cannibalizing their partner stars. This is, by the way, a map of the sky with integral, which it took 17 years to gather enough light to produce this map. But I think it's a pretty awesome thing to see. And I've been lucky enough since in my time here at Berkeley to be part of a project following up on these sources. We don't know what all of those sources are in that image I was just showing you. So by following up, taking longer exposures and doing some analysis on that data in just the X-ray, we can begin to understand what some of these sources are. At least 2 of them we've shown recently to be white dwarfs that are eating their companion stars. One of the ways we know that is by basically doing a search for any periodicity in the light curve. If you look at how the light from the source in X-rays is varying over time, sometimes those variations can be random. And if they are, they sort of look like the bottom of this plot here, where it's just random small spikes. But sometimes it can be varying in an exact, precise signal, sort of like a pulsar with what a neutron star will do, or if I flash a light at you on and off once every second. And we're seeing those white dwarfs do exactly that, except it's almost 600 seconds for the top one, and closer to 700 seconds in the bottom one. These are the spin rates of the white dwarfs. We're actually seeing that part of the material falling onto the white dwarf go in and out of our field of view as the white dwarf spins around. Another way we can do it, and one way we can actually measure just in X-rays the mass of the white dwarf, is that if we look at the spectrum of light coming in X-rays, this is a little bit of a confusing plot, but the general idea is the light from on the left in the X-axis is going to be redder light, lower energy light. The light from on the right is going to be higher energy light, or bluer light, but in this case we're in X-rays. So if you can imagine red and blue X-rays, that would be the way to do it. And then the y-axis is just how much light you're getting at every wavelength, or in this case, every energy. And I just took a model that we have for measuring white dwarf masses, and I input a bunch of different numbers. So we're starting at 80% on the bottom to 140% the mass of our sun. And not only does the total brightness change, as you'd expect it to, 140%, the most massive white dwarf is the brightest here in X-rays. What you also see is the shape changes. So on the right side of this graph, you see the bottom curve start to slope off and slope down at 80% the mass of the sun. If you go on higher up, you can see that it's a little bit flatter on the right side of that curve. Higher and higher up, you can see it gets flatter and flatter. That point where the curve starts to slant down and fall off to the right gets further and further to higher and higher and higher energies, the more massive you go. And this red shaded region is just the telescope I work mostly with, which is NuSTAR. So I have a fun little picture of NuSTAR. It's an X-ray telescope that's been in orbit for just over 10 years. We got to celebrate its birthday last summer, which now that I say that, it makes me realize that its next birthday for 11 years is coming up in just a few weeks. NuSTAR, the X-ray telescope, is particularly good at this because it can see all the way up to those higher energies, right where those curves start to fall off. But even for the most massive white dwarfs, you don't really see that cutoff anymore. So it gets a little bit harder to measure white dwarf masses as you get closer and closer to that mass limit. This is what the spectrum actually looks like. So there's lots of extra detail in here, but if you just look up on the top right of each of these 2 examples here, this is a paper I published a couple years ago, or last year now that I think about it, which is only about 8% more massive than our sun, this white dwarf. And you can see that it's falling off on the right-hand side of that top. If you compare that to a paper my boss wrote on a source that was 38% more massive than our sun, you can see that it's flat all the way at the top right part of that chart. So by basically fitting the spectrum and looking for how much curve you get off to the right, you can get a pretty reasonable estimate of the white dwarf mass, thanks to these material falling onto a white dwarf and heating up and shining in X-rays. These are just 2 examples. Just this month, we published a 3rd paper, which again is showing a flat top right portion of that chart, which means this is another almost at the limit, really massive white dwarf. And indeed, this is another one that's really massive. To summarize all of those numbers and how we go about measuring in X-rays a white dwarf mass, those 3 different charts I just showed you are the 3 green numbers there. J15038 is the one that just came out. J14091 is the one that my boss had done earlier, and 18007 is closer to a sun, the mass of the sun. So it's a bit of a normal, or closer to a normal white dwarf. There's a bunch of other white dwarfs plotted that you don't necessarily have to worry about. But what we've noticed is, because we're following up on these integral detected high energy X-ray detected sources, we tend to find unusually massive white dwarfs in X-rays. We've only done the analysis on 3 of them. There's a 4th one coming out. It's another massive one. And there's about 100 other sources that we plan to follow up on from these integral surveys, that all sky map with all those point sources I showed you. We're sort of biasing ourselves to only finding really massive ones and ignoring the less massive white dwarfs, which I think is the coolest. We've sort of stumbled into accidentally a really great way to find extra massive white dwarfs. Just to put this into comparison with those other 2 sources we talked about earlier on, ZTF J1901 was the one that had all the newspaper articles written about it. That was about the size of the moon, whereas Corona Borealis is the one that we first saw as a nova in 1866. Those are both up there in terms of the mass, but you see that these green sources were finding massive white dwarfs right in line with the most massive ones known. Although maybe the uncertainties are a little bit bigger than what we've seen before. Just going back to this map, I mentioned this, more than 100 of these sources we haven't actually classified yet. Most of those are going to be black holes and neutron stars, but maybe 10 to 20 of them are going to be white dwarfs. And if that fits the sample we've seen so far, we might find quite a few more massive ones. Yes?
Yeah, if you look close, there's like blue and black in the background. What is that?
Just noise.
Okay.
Yep. That's just the threshold detection limit, and those are just bits of noise that come out the way this image was produced. Yes.
This may be beyond your the scope of the lecture. I suppose it's conventional wisdom that white dwarfs accrete from other stars. Do neutron stars and black holes accrete from white dwarfs?
Yes, they do. It's not often seen, but we call those ultra compact binaries. And yes, that's a thing that's seen as well. Sort of the giveaway for that is when you see a black hole or neutron star X-ray spectrum, but then you look at it in other parts of the wavelengths, you're not seeing any hints of hydrogen and helium there, which you always see with accretion when you're stealing material off a normal star.
Right.
And it's because that companion that it's eating doesn't have hydrogen or helium. It's just carbon, oxygen, or heavier elements. And those are the spectral lines that you see. There's one more question.
Yeah, just sort of recapitulate the generation of the X-rays was from basically charged particles, electrons.
Or it could be thermal as well. It's both. So charged electrons or relativistic moving electrons will emit in a magnetic field a spectrum that would show up like this. So that absolutely happens. But it could just be the accretion disk around a black hole or neutron star is so hot that thermally it will emit X-rays,
Okay.
tens of millions of degrees or hundreds of millions of degrees.
So the result of infalling rate is deceleration, right?
Sort of, yeah, through a lot of different effects between different parts of the accretion disk. For here, for white dwarf, it's deceleration. It's just that shock.
I'm just wondering if you can drop down a level in terms of modeling of the generation process and the mass dependent or gravitational thing.
The gravitational dependence we've done a little bit of, and thankfully I get a nicely wrapped model where I don't have to worry about those technical physics, and I just get to analyze the data and work with it. So some of my co-authors would have better answers for you there. But yes, the physics going on within that sort of what I drew as the explosion above the white dwarf surface is definitely a little more complicated than I let on. Okay, so back to we have 100 more sources to go, so I think we're going to find a lot more white dwarfs that are really, really massive, which I think is awesome because, you know, just the one that's the moon sized got a ton of publicity because it was so special, because it was so neat, and we're finding those more and more and more. There might be a whole population of white dwarfs that we don't know about that are pushing that limit of the maximum possible mass that a white dwarf can be. Taking another step out and looking at the big picture, which I like this being a good big picture, our nice little galaxy there. Why do we care? You know, we have a good theoretical limit of a white dwarf mass. We haven't measured any that are technically above that. So what are we trying to do? I'm going to go back to the 2 different ways that we have white dwarfs interacting and matter falling onto a white dwarf. It turns out that, as I mentioned this earlier, you can have an explosion of a white dwarf. The entire thing can, in thermonuclear runaway, sort of ignite itself. And we call that a type 1a supernova. It's a very particular type of supernova. So people that have been studying supernova, you can have a supernova that's the collapse of a core of a really massive star, or you can have white dwarfs that, if they pass that limit, will ignite fusion and explode as a type 1a supernova. Turns out that if you were to rank all the supernova, and people can argue with me about this, it's, I think, a pretty good argument that type 1a supernova are the most important to what we understand, not just about because of white dwarfs, but because of what they have to do with our universe. When you take a step out, the coolest thing about a type 1a supernova is its ignition of 1.4 solar masses of material. That's the maximum limit for a white dwarf. You can't get a white dwarf any heavier than that. And when all of that material ignites all at once, right around 1.4 solar masses, then you know exactly how much energy is produced in that explosion. And type 1a supernova were classed as such because no matter where they are, they always seem to have exactly the same total energy output. They're remarkably consistent, whereas the collapse of a star into a supernova, it depends a lot on what that star was like. With these, there's way less variation. We call them a standard candle. And the idea in astronomy of having a standard candle, it's like the best possible thing you can have, because distances in astronomy are ridiculously tough to measure. So if you look at a star in the nighttime sky and it appears bright, is it just because it's close to you, or is it because it's actually an incredibly luminous object? Most of the time, it's tough to know that. But if you have a standard candle, you know exactly how bright it would be right next door. You know exactly how bright it would be down the street. You know exactly how bright it would be if it were in a distant galaxy. And just by measuring how bright it appears, you can measure all of those distances. In particular, the other best thing about type 1a supernovae is that they are ridiculously bright. So you can measure distances incredibly far out, even to distant galaxies. And why that's important in particular, I'm gonna just mention Edwin Hubble. I mentioned the Hubble Space Telescope. This is the guy it was named after. His biggest claim to fame is this plot right here, which is looking at galaxies within our universe and then measuring the distances. He was using a different standard candle than type 1a supernovae, but he was also measuring, which we can do because of the Doppler effect, how fast those galaxies were moving away from us. And he was just looking at a handful of galaxies, and he was expecting to see some sort of scatter, and he saw that there's a pretty close correlation between how fast a galaxy is moving away from us and how far away it is from us. And this was the first point in evidence that our universe is expanding. It's come a long way since then. In fact, a few wrenches have been thrown into the mix. On entirely different scales, you can measure Hubble's law, which was what that correlation is, and it's actually way closer. It's a way better correlation the further out you get, and the further back you look into our universe. But in 1998, a grad student, and I forget where he was looking at type 1a supernova data, and he noticed that by measuring the distances to those galaxies, he was starting to move away from the curve. If we had 0 right here, that would be perfect agreement with Hubble's law. And he started noticing as you got to higher and higher and higher redshifts, those points started to get further and further away from 0. A couple other groups saw this at exactly the same time. 3 of those people now have Nobel Prizes. And this was the first evidence for the acceleration of the expansion of our universe. If you've seen plots of the total energy makeup of our universe, most of it is not even dark matter, but dark energy, which is what's driving this acceleration and one of the biggest open questions in science and astronomy today. This is right outside, so you can look at it. It's on the wall. But again, this is our current understanding of not just how our universe formed, but how our universe is evolving over time. In some part relies on measurements of type 1a supernovae. So understanding how massive a white dwarf can get is a huge question, at least in terms of checking in with ourselves and making sure that we understand our universe in the way that we do. I should just side note, by the way, there's a bunch of other bits of evidence for dark energy and that our universe is accelerating, but type 1a supernova is maybe the most direct way that we can see that happening. If you maybe don't care about the universe, that's too big, that's too far away, that's too head scratching. Well, you might think that gravitational waves are cool. We're listening to mergers of black holes and neutron stars for the first time. Actually, was it this week or last week that Nanograv released their results? Now we know there's a hum of the universe due to mergers of supermassive black holes in an entirely different frequency range than what we were listening to before. These are all black holes and neutron stars. There aren't any white dwarfs here, but there should be. And when we get further improvements to LIGO and Virgo and other gravitational wave detectors come online, or future generations of gravitational wave observatories, we might actually see gravitational waves from white dwarfs, and we can start to probe the physics of white dwarfs in the way that we've learned about black holes and neutron stars from these gravitational wave observations. And then finally, if you say, I don't care about gravitational waves, that's too much, well, we can come back to this image of our sun setting over the bay, right here at home. Our sun will become a white dwarf. White dwarfs are what like 95% of stars turn into. It's the ultimate fate of most of those points of light you see in the sky, including our one right here at home. That does it for my talk. Thank you guys so much for coming out tonight, even with the cloud.